A proposed advancement in commercial aircraft design, the Boeing 797 blended wing combines advanced materials, digital systems, efficiency-focused engineering, and future aerodynamics. The blended wing design, BWB, which offers enormous internal cabin sizes, superior lift-to-drag ratios, and the potential for both commercial and military applications, stands out as a departure from the conventional tube and wing architecture, despite the fact that it is still purely theoretical. Boeing's vision of a high-capacity, eco-friendly aircraft that can transform medium and long-haul travel in the future is embodied in the 797 No. 1. Cabin configuration and design. Instead of confining passengers to a long, narrow tube, the blended wing platform enables the cabin to stretch across a large interior footprint. A slightly curved panoramic cabin with multiple zones that resemble open-plan areas rather than segregated rows could be found inside the 797. Seating can be arranged in wide arcs to follow the shape of the fuselage, improving sightlines and reducing a feeling of restriction. The aircraft can support a wide variety of configurations, including premium heavy layouts with lounges and social areas, high-density layouts for main routes, and modular zones that carriers can switch up according to the season. Aisle routes and emergency exits would be thoughtfully integrated into the curved geometry, with sporadic exits around the exterior borders to ensure safety while preserving the distinctive cabin design. Number 2. Interior materials and finishes. Sustainability, robustness, and acoustic performance would be given top priority in the 797's interior materials. Innovative thermoplastics, bio-based polymers, or ultralight composite panels could be used to make the main cabin surfaces. Seats may have long-lasting antimicrobial textiles, memory foam cushions, and frames made of recycled carbon fiber lightweight laminates that are resistant to yellowing, and scratches would be used for finishes that accentuate natural textures and muted, calming color schemes. In order to help passengers adapt to time zone changes and create a flexible cabin ambiance, LED-based ambient lighting systems would mimic the cycles of the day. Number 3. In-cabin entertainment and connectivity. More immersive digital systems are made possible by a blended wing platform's large interior volume and structural stability. High-bandwidth satellite communication, customized media environments integrated into seat shells or headrests, and panoramic display panels integrated into the cabin walls are all possible features of the 797 onboard cloud access services. Synchronized streaming and ultra-low latency Wi-Fi would be beneficial for work, gaming, and leisure. With graphics projected onto curved interior surfaces or personal XR devices, the aircraft may have mixed reality zones for entertainment or education, depending on the airline. Next-generation requirements would be satisfied by digital seat controls, USB-C and wireless charging standards, and power availability at each seat. Number 4. Noise reduction and cabin environment. Even without additional soundproofing, a blended wing aircraft reduces cabin noise by naturally placing passengers farther away from the engines. With vibration-dampening mounts, engine nacelles tuned for acoustic performance, and laminar flow aerodynamics, the 797 may further reduce noise. Through distributed ducts built into the wing body structure, environmental systems would precisely regulate the temperature. CO2 monitoring systems, humidity stabilizing devices, and advanced HEPA filtration can enhance air quality and reduce fatigue during long flights. Depending on passenger load and circadian cycles, lighting, temperature, and pressurization may change dynamically. Number 5. Cockpit and avionics. With its large panoramic forward view, touchscreen pilot interfaces, and AI-assisted systems, the 797's cockpit would represent a new generation of flight deck design. During times of high stress, pilots would use adaptive avionics, which prioritize important information while suppressing irrelevant information. Many conventional gauges may be replaced by head-up displays or augmented reality overlays, which project traffic, terrain awareness, and synthetic vision straight into the pilot's field of vision. Predictive automation and voice command features would reduce cognitive load without sacrificing pilot authority. In order to maintain operational integrity, the aircraft may be designed with future-proof features that enable reduced crew operations while maintaining human controls and redundancy. Number 6. Advanced safety features. Safety advancements would be built on a foundation of structural resilience, fail-safe automation, and layers of redundancy. Compared to a cylindrical fuselage, the 797's blended wing design distributes weight more evenly, improving crash survivability and reducing stress concentrations. The health of the airframe would be continuously monitored by sophisticated predictive maintenance technologies, which would identify issues instantly. Adaptive flight smoothing algorithms, envelope protection, and turbulence prediction are examples of flight control systems. Networked aircraft-to-aircraft communication, more sensitive weather radar, and improved ground collision avoidance would all contribute to increased operational safety throughout the journey. Emergency escape would be enhanced by fire-resistant materials, intelligent evacuation lights, and dispersed exits incorporated into the wing margins. Number 7. Performance and efficiency. A major aerodynamic advantage of the blended wing design is its high lift-to-drag ratio, which reduces fuel consumption when compared to traditional aircraft of the same capacity range. Payload efficiency and emissions could all be greatly improved by the Boeing 797. To reduce drag and noise, advanced turbofan or hybrid electric propulsion may be added to the upper fuselage or trailing edge. Long-range capabilities without compromising passenger comfort are made possible by the aircraft's roomy interior, which also accommodates large fuel tanks. Performance may be enhanced by aerodynamic morphing surfaces, real-time weather routing, and optimized flying routes. As a result, an aircraft will use less fuel to fly farther, produce fewer greenhouse emissions, and cost less per seat mile. Number 8. Exterior and aerodynamics. The fuselage and wings fully integrate in the 797's blended wing body architecture, giving it a smooth, tapered shape. As a result, there is less aerodynamic interference, creating a large lifting surface that increases efficiency and stability. To reduce vortex drag, winglets can be split-tip or elegantly curved. Placing the engine on the higher aft surface improves aerodynamic cleanliness and lowers ground noise. Drag is greatly reduced by the more laminar boundary layer airflow caused by fewer protrusions and improved transitions. The unique design of the aircraft also makes it suitable for a range of mission scenarios, such as carrying passengers, transporting cargo, and possibly low-profile military or humanitarian variants. Number 9. Baggage space. There is enough room for luggage and cargo thanks to the blended wing's internal volume. The 797 might have spacious, easily accessible cargo compartments dispersed throughout the lower center of the aircraft, instead of relying on the usual narrow belly holds. This setup can handle both bulk and containerized cargo, reduce turnaround times, and streamline loading procedures. Unusual freight and luggage can be safely and efficiently handled with automated or robotic loading systems. A balanced weight distribution reduces trim drag and increases stability. Number 10. Cost of ownership. The 797's long-term cost of ownership may be significantly lower than that of older aircraft, despite the initial acquisition prices potentially being high due to innovative manufacturing techniques. Ongoing maintenance expenses are decreased by using less fuel, having fewer parts, and using integrated composite constructions. Downtime is reduced by modular components, predictive diagnostics, and streamlined internal systems. Increased passenger capacity and fuel savings for airlines directly result in higher revenue potential and lower operating costs per seat. A shared avionics concept with other Boeing families might lower training costs, but specialized training would be required due to the unique aerodynamics of a blended wing number 11. Pros and cons. Pros: outstanding fuel efficiency as a result of enhanced aerodynamics. Innovative cabin layouts are made possible by the large internal capacity, decreased noise levels for both surrounding neighborhoods and airport visitors. Strong structural stability is guaranteed by the integrated wing body shape. Save money on fuel and maintenance to lower long-term operating costs. Safety systems and avionics that are prepared for the future for operations of the next generation. Cons. The cost of development and certification is high due to the uniqueness of the design. Problems with airport compatibility, such as gate fit and boarding procedures. Pilots need more training because of their special handling characteristics. The location of passenger windows is restricted because many seats might be situated far from the exterior walls. Adaptation to the special internal arrangement is necessary due to uncertain public familiarity. If this video helped you, please like, subscribe, and share it.